So today we move on to section 3.3, which has to do with extreme values of functions. So let's start off with some definitions. We suppose that f is a continuous function on the interval from a to b. And I've written this as an open interval, although it could be closed, it could be half open, half closed. It's just some interval of x values, and f is continuous on that interval. And we also suppose that c is some actual value in that interval. So c is some number between a and b. Then we say that f of c is the absolute minimum of f on the interval if f of c is less than or equal to f of x for all x in the interval. Okay, so essentially an absolute minimum here is just the lowest possible output you have over that particular interval. So if we look at the interval from a to b, oops, I'm just going to highlight this part here. This is the only part that we're looking at in this curve because we're only looking at the interval from a to b. So just look at these points along the curve. The absolute minimum is just going to be the smallest output you can get. Okay, so the smallest output that we could get would probably be, it looks like it's right about here. So for this particular c value, f of c, whatever the output is, right, I don't know what that output is, but f of c is the absolute minimum on that interval. Okay, and similarly, the absolute maximum of a function on an interval is just the largest possible output you have on that interval. Right, so if this is my function and my interval is going from a to b, right, I'm only looking at the portion of the curve between a and b. It's a little bit hard to tell actually, but depending on if we're including, it looks like actually here, if we're including the closed interval, or if we're including the endpoints here, the absolute maximum on this interval would be the output when x is equal to b. Right? This output is higher than any other output on that particular portion of the curve. So the c that we're looking for happens to be the endpoint here. So on this interval, f of b is the absolute maximum. Okay, now remember, absolute maxes and absolute mins are outputs. They're not the x values, they're the y values, they're the output of the function. So if this was, I don't know, 7 or something, right? If the output here was 7, then we would say 7 is the absolute maximum. And over here, if my absolute minimum here was at this point and had an output of, I don't know, 2, then we would say 2 is the absolute minimum. So absolute maxes and absolute mins are outputs. They're y values. They're not inputs. Okay. Now, we also similarly can define a local max or a local min, which means if we look at the curve altogether, if we look at the entire curve, we say that a particular output is a local max or a local min if it's the absolute max or min for some interval around it. So we'll see in the picture what that looks like shortly. But one thing to notice is that the function may or may not have an absolute max or an absolute min if we only look at an open interval. So as an example, let's say I were to graph here's my A and here's my B. It could be that we have vertical asymptotes at both A and B. So if we were to look at the, maybe the function looks something like this. Okay. Right, if we were to try to find the absolute max or the absolute min on the interval a to b, the open interval, there is no largest output, there is no smallest output, right? So for any, you could always find a larger and larger and larger output by choosing an x value that's closer and closer to a. And similarly for finding smaller and smaller outputs for choosing x values that are closer and closer to b. So on this open interval from a to b, there is no absolute max or min. So if we were to instead only look at closed intervals, does that mean that there's always going to be an absolute max or min on a closed interval? Well, as it turns out, the answer is almost yes, except we need one more assumption here. And that assumption is that if f is continuous on a closed interval from a to b, then we can conclude that f does have to have an absolute minimum and an absolute maximum on that interval. And that assumption of continuity is important because, again, otherwise we could look at that exact same scenario we were in the last case, right? That graph that looked like an asymptote here at A and another asymptote here at B. And maybe your graph looks something like this. And I don't know, maybe it goes like this on the other side and this on the other side. Well, if we were to choose some larger interval, let's say from, let's call this U to V, again, on the closed interval from U to V, this still doesn't have an absolute max or an absolute min, because we can still choose arbitrarily larger and larger and larger outputs and smaller and smaller and smaller outputs as we get closer to A or get closer to B from the left and the right. So on this closed interval from U to V, there is no absolute max or min. And the reason that this theorem doesn't apply here is because this function that I drew, this f curve, is not continuous on the interval from U to V. It has these asymptotes here. So it is important that we assume that the function's continuous, but if we know that it's continuous on this closed interval, then this theorem allows us to conclude that the function does have an absolute max and an absolute min on that interval. Let's look at an example. Okay. So on this graph here, we want to find the absolute max and the absolute min of this function on the interval from -3 to +3. So first of all, let's just look at the interval that we're looking at here. We're only looking at x values between -3 and +3, so I'm just going to highlight that part of the curve because it's the only part of the curve that I care about. I only care about x values between -3 and +3. And so what I'm looking for is I'm looking for the absolute max and the absolute min, the largest output of the function and the smallest output of the function over that interval, over that shaded pink region. Now remember, the theorem only applies if this function's continuous, which it is, right? We can see that this is a nice smooth curve. We don't have any holes or asymptotes. We don't have any jumps. And so this function will have an absolute max as well as an absolute min. How do we find it? We'll just look for the largest possible output and the smallest possible output. So what's the highest point that this curve reaches over that interval? The highest point it reaches, it looks to me to be just about here. Okay? Now the x value at the absolute min would be -1, but remember, absolute max. Absolute maxes and mins are y values, they're outputs. So the absolute maximum is this output right here of 2. Okay, now what's the lowest that you get on this curve? What's the lowest output you can have on this curve? So if we followed along this curve between -3 and +3, what's the lowest output that you get? Well, it looks like you get the same thing either at -3 or at +3. You get that same output of -1. Right? Again, we don't care about the x values for absolute maxes and mins, we care about y values, about outputs. So the smallest output you have on this shaded pink area of the graph is a y value of -1. Okay. Now for part B, it asks us to find the local max and mins of this entire function on R. So remember, a local max or min is just anything that could be an absolute max or min on some interval around that x value. Essentially what we're looking for when we're looking for local maxes and mins is we're looking for peaks and valleys on the curve. Right? If you think about this as a mountaintop, any peak and any valley would be a local max or a local min. Okay, so we have a peak here at this x, or at this output of 2, so we'll say f of -1, which is equal to 2. We have another peak here at x equals 2. So we have another local max at f of 2, and it looks like my output there seems to be somewhere between 1 and 2, so we'll call it 1.5. And finally, those are our only two peaks, but we have one valley over here at x equals 1. So that's our local minimum. And the output at 1 is actually equal to +1 as well. So on this graph, we have two local maxes, right, at these two peaks, and one local min at this little valley here. Okay, so in the next video, we'll talk some more about extreme values and talk about the extreme value theorem.